Tale of Two Involutes. I wanted to see if the involute of an evolute was the original curve. Well, okay, so we need to see what an evolute is, then what an involute is, and then take the involute of an evolute, and I use an ellipse for my experiments. Now, an evolute is a unique curve that has a transparent geometric and analytic interpretation. And I've done this several times in the past, so I was comfortable with evolute, but I had never done an involute, so that's a different story. So I first decided I would find the involute of my ellipse just to be sure I understood what involute meant. And an involute also has a geometric and analytic interpretation, and we'll see that. But it turns out that a curve has many involutes, and these form a family of parallel curves. So we got to make sure we understand what a parallel family looks like, it is all about, how it's described. Then finally, I will find the involute of the evolute of the ellipse, and that's the quest that motivated this study. So if the two terms, evolute and involute, have been wisely chosen by the math community, then the involute of the evolute should come back in some sense to the original curve, and the extent to which that's true is the essence of this webinar. Let's begin with the appropriate set of definitions that we'll need. Evolute. Here is an analytic representation. R is the radius vector or position vector representation of the curve. Little r is the radius of curvature, and n is the principal normal. Involute, analytic representation. S is arc length. It's the arc length function, and t is a unit tangent along the curve described by r. Parallel curves. D is a constant. R plus dn. So here you have analytic representation, and here you have a geometric interpretation. Evolute. Two descriptions. Locus of the centers of curvature, or, equivalently, envelope of the family of normals. Involute. A curve traced by the end of a piece of string, unwound tautly from the curve. I have draw you some pictures and show you what that looks like. I had to draw them for myself to see what it looked like. Parallel curve. A curve that's everywhere equidistant from the base curve R. Turns out a plane curve has many parallel curves, a unique evolute, and many involutes. The involutes of the evolute will form a family of parallel curves, one of which is the original curve R. So let's look at the evolute of an ellipse. And by way of preview, I've got some pictures. This green curve is piece of the ellipse. We'll have an ellipse that goes like this. Origin, O. Position vector to the ellipse, R. This goal vector is along the principal normal, but it's scaled by the radius of curvature, so it goes right to the center of curvature, and this black circle is circle of curvature at this point. Vector addition, R plus little rn puts you at this center of curvature, so the blue vector is going straight to the center of curvature. As the point of contact moves, the center of curvature will move and it will trace out a locus. That locus is the evolute. The locus of the centers of curvature. Let's look at that. In red, you see an ellipse. In green, there is a circle of curvature making contact with the ellipse. The gold point is the center of curvature for that circle of curvature. As I move the contact point, that's what this slider will do. It will move that contact point. The gold dot will trace the evolute. So point of contact is up here in the first quadrant. The evolute is being traced in the fourth quadrant. When the tracing is in the third quadrant, the point of contact is in the second quadrant. So just follow that once or twice so that we can see the tracing of the evolute. Now, what do we mean by this envelope of the normals? So again, let's use a picture to do that. This is an animation. Here is the slider, controls the animation. The green line is along a principal normal. And I'm looking at the principal normals drawn in the fourth quadrant on the ellipse. Notice that the green line is tangent to the evolute. The evolute's in black. It's tangent to the evolute. So there is a family of these normal lines. One point on the evolute is in common with one of the normal lines. That's what we mean by an envelope. The portion of the evolute here in black is an envelope of this family of green normal lines. Okay, so two alternate descriptions of an envelope, of an evolute, and a picture to show what this really means. Well, pictures are great, but now it's time to do some calculations. Let's obtain the evolute analytically as the locus of the centers of curvature. Here's how I did it. First of all, I worked in the student vector calculus package. This command causes vectors to be displayed as columns rather than as sums over basis vectors. So here's my ellipse, 2 cos t sine t. So you can see that the semi-major axis is 2 and the semi-minor axis is 1. So parametric representation of the ellipse. Principal normal, I'm using Maple's built-in principal normal command. The argument has normalized in it, then you get a unit vector. And a radius of curvature command. So there's the radius of curvature. Then I used the space curve command in this student vector calculus package, and I prefer this command over the older space curve command spelled with all lowercase letters, and that's in the plots package. The problem with that is it only works for three-dimensional curves in R3. When you want to draw a curve in R2, you use a completely different syntax. You use the plot command with completely different syntax. This space curve command in the student vector calculus package uses the same syntax you represent the curve as a vector, whether it's two-dimensional, three-dimensional, you use the same syntax. So I think this is a much nicer way to draw a curve. So here is the evolute. Here is the ellipse, and I put them both together, and we get this picture of the ellipse and the evolute. Well, what does r plus little r n look like? Here is a vector representing the parametric form of the evolute. And keep this in mind, because we're going to see this again and we're going to obtain this in another way. 3/2 cos cubed minus 3 sine cubed. Okay, now let's look at the envelope of normals. So we want to get the evolute as envelope of normals. Here is the description of the ellipse, 2 cos t sine t. And I want to make this a function, and I want the independent variable to be t. And I want u and v instead of x and y. X and y will be the coordinates along a normal line. U and v will be the coordinates of a point on the ellipse. And since I'm describing the ellipse parametrically, if I want a slope along the ellipse, I have to use v prime over u prime, and I'm going to call that m. Then I can write the equation of a normal line. You see the minus 1 over m, so negative reciprocal of m, x minus the x coordinate of the point on the ellipse, and this is the y coordinate, y minus. I brought everything over to one side. This function is a function of x, y, and t, the parameter t. And this represents the family of normals. Now, to get an envelope of a family, you solve simultaneously two equations, set f equal to 0, and the derivative with respect to the parameter equal to 0. And so I solved for x and y. Then I put them into a vector so that its components would come out to be 3/2 cos cubed minus 3 sine cubed. And then this command will create an animation that we've seen already. It's the animation of the normal lines that touch the ellipse in the fourth quadrant and are tangent to the evolute in the first quadrant, and the evolute is the envelope of these green normal lines. As I said, I was comfortable with evolute, needed to bring myself up to speed on involute. So let's get up to speed on involute. X squared plus 4y squared equals 4 is the Cartesian representation of the ellipse that we described parametrically. It has semi-major axis 2 and semi-minor axis 1, and it's oriented like you see here in these two pictures here. Okay, here is the ellipse. This gold color curve is an involute. That's what it looks like. All right, what is this piece of string business? You take a piece of string and you wrap it around the ellipse. Here, F is where the string is fastened. P is where I'm going to put the pencil. And I unwind that string, keeping it taut. And so here is another animation. You'll unwind the string, keeping it taut. And the pencil will trace out the involute. Now, the green portion of the ellipse has arc length S, and that's a length of string, and you're pulling it tight, so the green line has the same length. And because I'm holding the string taut, this green string leaves tangentially from the ellipse. So here, let's increase the number of frames, and you can see how the involute gets traced with this geometric idea of the piece of string unwound tautly from the ellipse. And you can tell that if this point P had been altered, had been moved, then the involute would leave from a different point. It would be up here. It would start from up here. And that's how you get this family of involutes. It just depends on where you start the point P at which you hold the pencil. That's why R minus ST describes the involute, but it's a little bit trickier than that. We want another picture. So this picture shows how the vectors in R minus ST behave. We have ellipse, position vector to a point on the ellipse. M is the point where the string leaves the ellipse. S is arc length, and these two green curves, one's a curve, one's a straight line, have the same length. P is the point that where you put the pencil, and that traces the involute. This is the tangent vector. This minus sign takes the arc length and flips the vector the opposite way so that it points to the point P. So that minus sign is essential. How about some calculations now for involutes? We need a unit tangent vector along the ellipse. That's this goal vector here. We need to find that. So we use built-in tangent vector command. There's the tangent vector. Now we need arc length. Well, think about how you get arc length. If R, describing the curve, has components x and y, you need parametric, so you take derivatives, you square the derivatives, add, take the square root. And that gives you the element of arc length, provided you put a differential at the end of it. Well, the stuff here is really the derivative of r with respect to t norm. So I will call that quantity element arc length. It comes out to be this. Then you have to integrate to get the arc length function. So I'm going to integrate the arc length function from t equals 0, the parameter equals 0, to some stopping point, a. Well, Maple will not know the relationship between a and t, so you better tell it, give me all the solutions. Now, you get a positive, a negative, and a 0. Well, we only want to look at a positive. So this simplify trims down the size of this expression, but it's now an expression in a. I would like to return that to an expression in t, and so I make that substitution. I'd like to look at what this expression for the arc length s is like. So between 0 and pi, this is what that expression looks like. You have elliptic functions. You should expect that. we know that when you compute the arc length on an ellipse, you get elliptic functions. Between pi and 2 pi, it looks like this, because Maple is counting how many times it's gone around. This is the floor function. It gets a little bit more complicated. So I drew its graph. Well, here's its graph. It's a monotone increasing function. And this is the graph of the evolute that I get if I use the formula r minus st. And so, how do you get a family? Well, if you add to the arc length when you start, it's going to be down here. If you subtract from the arc length when you start, you're going to be up here. So these three curves were drawn with a equals -1, 0, and 1, just to see what the members of the family might look like. So I think we're ready to tackle the involute of the evolute. The first question that I asked myself was, could you actually recover the ellipse if you knew the evolute? Here's the ellipse, parametric form. And this is what we discovered the evolute to be. 3/2 cos cubed minus 3 sine cubed. So, if you know E, can you determine R? Well, here's an R explicitly, but there's R hidden in N, and there's R hidden in little r, which is the radius of curvature. So if you put the pieces together, you're looking at something like this. Describe the unknown R as x of t, y of t, and use over dots for derivatives. This is what the right-hand side looks like. And if you know E, well, this is a pair of coupled differential equations. Now I'm going to take the initial conditions that match the ellipse that I started with, so I'm kind of cheating here. So we have these two differential equations and these initial conditions, and I threw that at dsolve, and lo and behold, I got back the original ellipse. So, in a sense, yes, you can recover the curve from the ellipse, from the evolute. Recover the curve from the evolute. Okay? But I cheated a little bit because I used the initial conditions for the curve that I started with. So, can we compute the involute of the evolute? So, I'm going to define parametrically the evolute that we've seen several times already. And now we're going to go through the process of obtaining the involute of this curve. I need a tangent vector. This is what the tangent vector looks like. You see the absolute values in here because these signs change while you're trying to go around the ellipse. So you have to pay attention to the signs. The absolute values are important. We need arc length. So we use the same trick we used already. Element of arc length, take the derivative and get the norm. That's what it looks like. And you see there's absolute values in there too. And then we have to integrate. And I tried several different approaches to this integral. I've tried definite integrals of different types and so forth. What I found worked the best was to take the indefinite integral, and you'll notice there's a signum in there. You got to pay attention to signs. This S allowed me to draw the involute that I expected. But if you graph S, it looks like this. It's discontinuous. Depending how you interpret the discontinuity, you either say it's not monotone, or it goes off to infinity and comes back around. So it is, at least it's monotone, but it's discontinuous, and it's negative. Down here it's negative. Why is that the one that works? Here is E minus st. 0 to pi, I get back the ellipse. Pi to 2 pi, I get back the ellipse. Well, pi is 0 pi, the singular points, and Maple Simplify gets all unhappy about the singular point. So by skipping the singular point, you can at least see that when you're away from the singular point, you get the result you want. And then otherwise you have to take limits, and you're just going to get this messier than it needs to be, because I'm just trying to get an idea across here. But what bothered me was, why does this negative stuff work? Why did it take this negative arc length to make this work? So I had to draw some pictures. Remind you how the ellipse gets drawn and how the evolute gets drawn. Okay, first quadrant here, fourth quadrant here, third quadrant here, second quadrant here. Now look at this diagram. Now I'm going to see what happens when you draw the involute of the evolute. So again, this is animation. Red is the radius vector. Black is the tangent vector along the evolute. Notice the tracing is downwards, so the tangent vector is going to point downwards. The arc length, being positive, has a minus sign in front of it. It flips the direction of the tangent vector, and so the goal vector is now pointing back to the ellipse, and so the involute of the evolute is tracing the ellipse. But let's go a little further. Let's look over here. Position vector in red. The evolute is traced upwards, so the black vector is the tangent vector, and it points upwards. If the arc length were positive, that minus sign in front of S would flip this green vector, and it would point down here somewheres, and it would not point up here to the ellipse. And I got that picture many times, which is why I said I got to figure this out. That's why the arc length being negative works, because you got a minus sign in front of that, and the arc length is positive, and it keeps the tangent vector pointing in the same direction, so you get this green vector that goes up here to the ellipse in the second quadrant. And it wasn't until I drew this animation that I could finally say to myself, oh, I finally understand this. So let's now think about this family of involutes and the notion that you're getting a set of parallel curves. So, all right, so let's just look at parallel curves. Okay, and let's use the ellipse. So curves parallel to the ellipse. So it's r plus d n, where n is the principal normal. Now remember that the principal normal points inwards. Here is an animation. This slider controls the value of d, and notice that I'm using negative values so that dn, d being negative, points outwards, and you see closed curves that are oval. If you go inwards, if you get deep positive, you get funny stuff on the inside and much harder to visualize as being parallel curves. So this is a family of curves parallel to the ellipse. That's what they look like. And I was curious, are these things themselves ellipses? And I said, oh, how am I going to do that? So this is what I ended up doing. I evaluated this curve, r plus dn, at this point and this point. I wanted to know the length of these two lines. Were they semi-major and semi-minor axes? Okay, so here are the 2 points. And then I said, okay, I've got expressions for this vector, 2 components here, little v, script v1 and script v2. If these curves are ellipses, then division of this component by this length and this component by this length squared and added should be 1. Well, this is a mess. This is really a messy thingy. So I graphed it, and I looked at the graph and said, the only way it's one is when d is 0. Okay, so these are not ellipses. I just had to satisfy myself that those things were not ellipses. They're parallel curves. They're not ellipses. So let's look at this family of involutes. So E minus ST. But what's going on here? Remember, S was the arc length function that worked. Signum in front of the A that causes us to have a family. Well, when S is positive, you want A to be positive. So you want the sign of S in front of the A. When S is negative, you want that minus sign to be in front of the A, because I'm going to use A. I'll just take A positive. See what happens. Okay? So this then represents a family, the parameter of the family being A, of involutes. So let's let A vary. And lo and behold, we get a family of closed curves that look very much like this family we saw up here. Now, are they the same family? And that's the last part of the investigation. Okay, are the two families of closed curves the same? How will we establish that? Well, I looked at the first family, the one described by V, at one point. And then I looked at the other family, G, at the same point. And I looked at these two expressions and I said, you know what? If A and D were simply related by setting A equal minus D or vice versa, what would happen? Well, let's take the second family, change A to minus D, and compare it to the first family, and let's look at it between 0 and pi. They're the same because the difference evaluates to 0. Let's do the same thing on pi to 3 pi over 2. You get 0. And let's do it from 3 pi over 2 to 2 pi. They're the same. And remember, you got these singular points, and you can, if you think carefully, those singular points were when you hit the coordinate axes where you had cusps. And then you have to take limits, and it would just take us off on a tangent. The two families are the same. So, involutes, evolute, are curves parallel to the original curve, and one member of that family is the original curve.